Hello everyone, this is Francesca Vigliani from Cloud Academy. We are here today once again with the one and only Andrea Giussani, who will guide us through the world of machine learning pipelines. This session is meant to give you an overview of what that looks like. So thank you for being here with us today. I'm seeing several people who already attended webinars that Andrea led in the past, so welcome back. And of course, before passing the baton to Andrea, you know I have to make the usual housekeeping announcement, so bear with me a couple of minutes. This session is being recorded and will be shared with you via email as soon as it is available. And by the way, we also upload past webinars to the Cloud Academy website. So if you're interested in seeing what other topics we've covered in the past, head to cloudacademy.com/webinars and have a look, see what interests you. We have several webinars that Andrea did in the past. We have a whole series on pandas called Pandas Like a Boss. And then the most recent one on Fast API. So just have a look and see what interests you. You should be able to see a chat box here. You can add your questions in there and we'll tackle them during the final Q&A. And did you set up the environment in advance? In the email and in the sign up page that you've seen to register for this session, we added the link to a GitHub repository. So please, if you haven't already, do retrieve that link. I will also post it here in the chat. And make sure to clone it on your local environment. And if you already did it, then please pull up the latest version. All right, I think that's about it. Enough with the boring stuff. Let's get down to business. Over to you, Andrea.
Thank you, Francesca. Welcome everybody first. It's a pleasure to see so many people even today, so thank you for participating. And as usual, just a brief introduction of myself. I'm a data scientist here at Cloud Academy, where I mainly focus on the development of machine learning algorithms to provide state-of-the-art solutions to improve the quality of our product. You can reach me out on LinkedIn, and you can visit my website for updates on machine learning or Python in general. This is a hands-on webinar, so I will perform all the necessary steps live with you. But don't worry if you are not able to follow all the steps live, because I will upload at the end of the webinar the full code on the GitHub repository that you should have in the URL. You should have the URL in the registration email. So the agenda goes as follows. We're going to understand today's topic and the learning objectives as well. And then I will try to also give you an overview of a general supervised machine learning pipeline with scikit-learn, basically. And then I'll try to also give you an idea of the environment and the data we're going to use today. Okay, so today is the first machine learning webinar we are doing here in Cloud Academy, and it's gonna be pretty introductory. So this is scheduled for anyone who wishes to learn more about machine learning and to get an idea of what machine learning is from a backend point of view. Build, in particular, a standard supervised machine learning pipeline using Python as the backend language. And as I mentioned before, we're going to use the scikit-learn Python library to perform all the necessary steps. And last but not least, this is quite an introductory webinar, especially to give you a taste of what we're going to perform during our 5-episode machine learning webinar series starting in September 2021. As usual, since we are using Python as a backend language, it is suggested from your side to have an intermediate knowledge of Python, or the Python language. And last but not least, the software used during this webinar is 100% free and open source. So definitely you don't need to care about cost or buying a software in order to perform all those necessary steps. Okay, so at the end, today we are going to build a supervised machine learning pipeline using the scikit-learn Python library. And at the end, you will get an idea of what machine learning is from a backend point of view. But in particular, you will understand the importance of preprocessing in a machine learning pipeline. You will be able to fit independently a fit regression model to estimate the house median value. You will be able to understand and put in practice the scikit-learn pipeline object. And last but not least, we will try to get an idea on how model parameters tuning works in the backend. So, as I said, we basically want to build a supervised machine learning pipeline to estimate the median value of houses. And in particular, we're going to use the Boston dataset, which contains information collected by the US Census Service concerning houses in the area of Boston, Massachusetts. And as for the environment, we are going to use the Google Colab to perform this live session. If you don't know that setup, don't worry, I have written a README for you in order to set up the environment. And if you are familiar, don't worry, and you can find all the details on that README in order to get everything set up and up to date from your side. Okay, so let's get started, and let's jump into a Google Colab session. I have already opened one, so be sure that you have a similar environment as the one that you see here on my screen. And what we are going to do now is actually performing a series of steps that I briefly mentioned before. And as first, we are going to basically mount our drive inside our Google Colab session. As usual, you have to perform such kind of authentication. Should be pretty standard from your side. And we're going to authenticate. And once you get that, you just need to copy and paste such kind of code. And once you enter the code, you will be authorized to mount your drive, your Google Drive, inside the Google Colab. Why is that? Because actually we need some data in our pipeline in order to perform the necessary steps to build and fit a machine learning pipeline. So once we have built that, what we can do is the following. We are gonna take the data that are actually in my local drive, in my Google Drive. They are placed somewhere in some folders. Obviously, you should know where you put the data. In my case, is in CR webinars, and then you get here introduction to machine learning pipelines. I just copy the path, and I'm going to read that data set using pandas, and in particular the read_csv function. And I store the data into the Boston data frame object. Yes, it's correct. Here we go. So we can inspect the first 5 rows as usual to understand the data we have on hand. And in particular, you see that we have a few columns here from crime to Elstat. They are actually our feature or independent variables, and the median value is our target variable. So once we have understood this, we can actually split the data, and in particular, we are gonna take the Boston DF and we drop actually our target variable in this way using the drop method, and in particular, we perform this with respect to columns. And last but not least, we are going to actually take the median value, the series inside our data frame, and we store that into the variable y. So once we have such kind of variables, namely variable x denoting all the features in our data set, and y denoting the series of target variable, we can actually perform our steps to build and train a supervised machine learning pipeline. Just note, please, that in this introductory webinar, I'm going to take into account just a supervised case, but you can find in our content library different content, in particular courses and labs, that describe also unsupervised pipelines. So check it out in our content library if you're curious. Okay, so in order to understand why scaling is so important in a machine learning pipeline, what we can do is actually we can plot actually the distribution for each single variable in order to understand the magnitude and actually the relationship between those variables. So in order to do that, I'm just gonna copy and paste here a snippet that is actually based on two graphical libraries, Matplotlib and Seaborn. And what we are gonna build is actually, we're gonna use the boxplot function from the Seaborn library, and we are gonna basically plot the distribution of each single variable with respect to the median value. So at the end, we get this nice plot. And in order to understand why scaling is important, you just need to read this plot. And what you see is actually that we have a few features, in particular taxes, this B feature, and age, that are pretty different from the others. The others are shrink towards 0. Instead, those features are expressed in hundreds. This means that they share different scale, and therefore, when we want to fit a model, in particular, for instance, a linear model in machine learning, if we have such kind of magnitude, the different magnitude among features, the one with higher magnitude might give you a bias in the estimation of the parameters of the model. So we don't want that. We want to homogenize the data. And one possibility, or better, a strategy, is actually to standardize the data. If you're curious on different strategies for machine learning pipelines, you can check the course Building Machine Learning Pipelines with scikit-learn Part 1 that we have in our content library. Today, we're going to focus on just one particular case, and in particular, we're going to use the standard scaler, which is de facto the most popular scaler in scikit-learn. And what it performs is actually is going to subtract the mean for each single feature, the mean obviously of that particular column, and it divides by the standard deviation. Just also, I want to highlight the fact that, in general terms, scikit-learn, the library that we are going to use for to perform machine learning here in Python, is actually built on two main classes. One class called transformers, that are actually used in the pre-processing phase. And the transformer is nothing more, it is characterized by two methods: a fit that learns some patterns about the data, and a transform method that transform the data according to the patterns that he learned in the training phase. And then you distinguish the transformers from the models. The models are instead characterized by two methods: a fit, which actually learns some patterns in the data, and a predict method that actually predict some labels on unseen data, on new unseen data. Today, the standard scaler belongs actually to the transformer class. And today we're going to use both transformers and the models in order to perform a whole machine learning pipeline. Okay, so let's scale the data. Before doing that, actually a very important steps in a machine learning pipeline is the following. We get a set of data, and while we want to fit a model, we want also to be sure that our model fitting is somehow good. And in order to do that, we have to evaluate the model during the training phase, or actually better, after the training phase. And to do that, we can build a test set. We can extract a test set from our data in order to actually train a model on a part of those data and test the data on data that were not used during the training phase. So it's very important that we keep the training and the test set separate so that we are able to evaluate the trained model on a test set that was not used during the training phase. And to do that, we can import from scikit-learn, in particular the model selection. We import the model selection submodule. We import the train test split function. And the train test split function is pretty useful since it allows us to build a train and a test set starting from our two variables x and y. In particular, now we can also produce 4 different variables: an x train, an x test, a y train, and a y test. And in particular, we are going to use again the train test split. And as I said before, we are going to take into account our features x, our set of feature x, and the variable y containing the target variable. And we specify, for instance, the test size of the splitting is 0.2, meaning that from our original data set, we keep the 20% of the data set to be the test size. And we also set the random state, which is an argument that allows us to set reproducibility inside the splitting procedure. And we set that as 42, for instance. So in this way, every time you run this code, this cell, the random state equal to 42 prevent the function train test split to produce different output. In other words, in this way, you will get exactly the same x train and x test as soon as you run this code. Once you have done that, we can actually perform the scaling procedure. So, as I said, the standard scaler is a transformer, and in particular, transformers are used during the preprocessing phase. And what you typically do is actually perform a scaling procedure before fitting the model. And one possibility is to use the standard scaler. It's basically the most popular transformer in scikit-learn. And even today, we're going to use it. And as I said before, the standard scaler performs basically two operations. Fit operation, where it learns some patterns in the data. In particular, it learns the mean of the feature and the standard deviation. And it transforms the data using those patterns by removing for each single feature the mean and dividing that number by the standard deviation. At the end of this transformation, you get a new data set or better, a new representation of the original dataset based on values obtained with the standard scalars. And why do I need the standard scalar? Well, remember, look at this picture. We have data that are not homogeneous in their magnitude, in their scale. So we want basically data to be somehow homogenized so that there is no major feature that dominates the model performance, the model estimation. So for instance, in this way, if we are going to fit a linear regression model, possibly we are going to get that this tax feature is going to be a very important feature compared to others. But possibly that is just because we are using a tax feature expressed in hundreds, whereas the others are expressed with lower scale. So what I can do is the following. I import a standard scalar, and actually we need to perform two operations. I'm going to define a scalar object, which is nothing more than the initialization of the standard scalar. And then I'm going to apply the fit and transform method directly to the scalar, in particular by using the training set. And I call this object xScaled, or better, I store that object into the variable xScaled. And just to be clear, I can also define new data set, a new data frame, sorry, which is nothing more than the xScaled object that I just obtained from the scalar. And I define also the columns, which is nothing more than the list of x string. And to give you an idea, the scaling has produced such kind of data. And just for comparison stuff, you can see the first 5 rows of the X train. And you see that now all the features share the same scaling. And you see that taxes can be compared with prime easily, whereas before taxes were expressed in hundreds, here was expressed in a lower scale. So once we have performed that, we can also, to be sure, we can also show this graphically. And in particular, you are gonna use instead of X, the scaled df. And the plot confirms our expectation. We have somehow homogenized the data. And so we are pretty confident that now we can actually fit a model. So this is not a KNN, sorry, it's a ridge. Sorry for that. We're going to fit a ridge regressor, not a KNN. So now once we have built a data set, we can fit a model. And obviously, the role of a data scientist typically is to be sure that the data are consistent, and therefore to perform pre-processing in the data set, which means data wrangling, data cleaning, etc. But more importantly, understand which model fit the best to the data. And therefore you have tons of possibilities. I have chosen a ridge regressor for this webinar for many reasons. A ridge regressor is actually a linear model that extends the standard linear regression model by adding a bias inside it. And in particular, a ridge regressor is a member of the shrinkage methods, which is a very popular technique in machine learning, in predictive analysis, to actually allow the estimated values to be a little bit biased, but the bias allows us to actually get values that are better somehow with respect to standard models such as linear models. And if you're curious, you can obviously check our content library. We have a great content on ridge regressions. Today, we're going to just use it as a tool to show you how to produce a complete machine learning pipeline. So don't worry too much about the technical details of the ridge regression now. You will have time to digest the concept later after this webinar. So the point is the following. We are actually going to use the linear regression, the ridge regression, and in particular in scikit-learn you have the models classes, and in particular you have a linear model submodule, and we import, as I said, the ridge model. And fitting a model in scikit-learn is pretty easy. What we can do is the following. We are going to initialize a ridge by just calling the ridge class. And then you just need to fit. Remember, a ridge is a model, and the model is characterized by two methods, a fit and a predict. So we just, once we initialize the model, we are able to fit directly that model using the training dataset. And in particular, you pass the X train and the Y train, easy. And with just two lines of code, you have fitted your standard model, your ridge model, which is a model, you know, and therefore it can be used to perform some prediction. And as you know, machine learning is used to perform prediction on unseen data. And therefore, once you have on hand the ridge model, you can actually apply the predict method on the X test. And then you get some values. And in particular, you can be sure that you have applied correctly the model by accessing to the score, and in particular to the score. The score by default used in a linear regression model by scikit-learn is the mean square error. So the one that you will see here is indeed that particular score, and the function requires two arguments, the X test and the Y test, and you get this score of 0.662. Okay, so what's the point? The point is the following, that if you so this model has learned some patterns from the train data, but as you know, we don't want to use the original data because of scaling. So actually what we can do is the following. We can actually take the scale df, and actually instead of passing the X train, we use the scale df. So I refitted a new model, and now look at this. I'm gonna use the model that was fitted on the scale data on the X test. Remember, the X test is a non-scale test set. I get some values, and you see that the values are pretty strange because you have negative 1,100 and something. So it looks something strange to me, and I can try to compute the score, the mean square error on that particular test set, and I obtain a very low score. So this is expected, and the motivation is pretty simple. I have fitted a model using scaling data, but then I use that model to predict on unscaled data. And this is not really a good strategy. So what we can do instead is transform the test set based on the scaler that we fitted before. And therefore I can pick the scaler and actually transform the data. And we pass those data inside the predict method. I expect now that those values will change brutally and that the performance will improve. So let's try to do that. You see that now you get better estimation. You see here, much better. And let's try to see the score. The score is still the same, yes, because it's not X-test, but we pass the unscaled data, the scale data. And here we go. You get 0.668, which is much better as a score. Sorry, I made a mistake, so sorry for that, because the score by default is not the mean square error. It is the R square, which is a number between -1, between 0 and 1. So a number R square equal to 0 means that the model poorly explain the data. R square equal to 1 means instead that the model explain completely the data. And therefore a number between 0 and 1 as the one that you see here is the one that you should expect when you run and you fit such kind of models. We got a 0.668, which is quite a reasonable number, which means that the model explain quite a lot our data. You can obviously use also the mean square error, and you can obviously compute that matrix, but for the moment, you just focus on the R square. Well, let me compute it. It's fine. It's pretty simple. We can import from the matrix. We import the mean square error. Mean square error. Here we go. And then you can actually also use NumPy in order to compute the square root of the mean square error. And the mean square error actually, let me check, but it should require let me check the y test and the y pred and the y test, obviously, but I don't remember the order. That's why I'm trying to check the help, the y true and the y pred. So the order is that one. I was correct. So what we can do is using the y test here and the y pred here. And here we go. So actually, with just a few line, a line of code, you were able to actually compute the mean square error. But again, remember, by default, you get R square. Okay. So once you have done this operation, now it's time to jump into the concept of pipeline. If you have paid attention, you have actually performed two steps: a pre-processing phase, where you basically transform your data from using the standard scaler, and then you use those transformed data to fit a model and to make some prediction on a test set. So what's the purpose of a pipeline? If you paid attention, we made a mistake before. The mistake was intentional from my side because I wanted to discuss with you about this particular case. And if you remember, I passed inside the ridge directly the X test, but I obtain a strange results, as you remember. And therefore, in order to fix that problem, we used a scaled version of the X test because the ridge was fit on a training set that was actually a training set that was not the original training set, but was the scaled training set. So this can be cumbersome somehow because you have to remember that the predict method was requires the scale data, and therefore you have to perform at each single every single call of the predict that you have to remember to use the scale data. Nicely, scikit-learn allows you to build a machine learning pipeline with just one single object called, strangely enough, pipeline, which allows you to actually make the process smoother, but actually much more readable from a base code point of view. And to do that, what we can do is the following. We are going to import from scikit-learn in particular, we are going to use the pipeline submodule. We import the pipeline object. And in my opinion, such kind of object is cool and possibly is actually the object, the class that distinguish scikit-learn from many others libraries in Python. And the pipeline is pretty cool and works as follows. So you just need to initialize a pipeline object. And what you have to do is to specify all the steps that you expect in your machine learning pipeline. And this set of steps are defined as a tuple, where the first element is the name you wish to assign to the step, in our case, scalar. And the second object is nothing more than the scikit-learn class that you want to use in that step, in our case, the standard scalar. And then you basically specify the second step, in our case is, for instance, I assign the tag model and I use a ridge model. So if you remember, this is exactly the same that we did before. We standardized the data and then we applied a ridge model to that particular data set. We store this into the variable ml_pipe, and look at now, with just one line of code, you basically pass the X train and the Y train, and all the dirty job will be taken into account for you by the pipeline object, by the scikit-learn pipeline object. So you just need to run this chunk of code. Basically, you feed the model, and you have fitted a pipeline object with the standard scalar and a ridge model. This means what? That then you can actually try to see whether you obtain the same result. And how can I check that? You have a test set, and therefore you can actually try to apply a ridge to a machine learning pipeline, sorry, to the X test. And you get exactly the same result as before. But now look, the code is completely different. You don't need to transform the test set as we did before, because the transformation is done in place for you by the machine learning pipelines, because it knows that every time a piece of data is passed inside the machine learning pipeline in this object, he has to be transformed by a standard scalar. And then you have a ridge model fitted with the training data on which we predict on those unseen new data. And that's pretty brilliant from my side, because it allows you to build machine learning pipelines, even complex machine learning pipelines, with just a few lines of codes. And believe me, you will start loving this kind of object as soon as you start building machine learning pipelines, because it's pretty useful from a developer, from a developing point of view. Okay, so the last thing that I want to mention is the following. We have understood how to build a machine learning pipeline from a backend point of view, but at the end, we have missed something. And in particular, we have missed the fact that a ridge is a model with some parameters. And the parameters are the one that I'm highlighting here, the alpha parameters, which controls basically the shrinkage effect, namely the bias inside the model. You have, for instance, this solver and the normalization argument, which can be tuned and can be tuned actually in order to improve the performance of the model. So for the moment, in this pipeline, we have used the standard values of the machine learning pipeline, of the region inside the machine learning pipeline. But obviously, you can go further and say, well, I want to set different values for my alpha, for instance, so that possibly the best model, namely the model that gives me the higher R squared, is not the one with alpha equal to 1, but possibly with a different value. And to do that, you have different ways to get that result. One way is to try to perform hyperparameter tuning. Another important step is the following. This score that you see here might be given by chance. What I mean is that you get a model, you get some data, you split the data, if you remember here, using this function, and with random state equal to 42. But possibly that split was given by chance because you set this random state equal to 42, and that splitting procedure produced a data set, a train and a test set, that gave you that score because of the splitting procedure. So in order to avoid such kind of bias, possibly induced by the splitting procedure, typically people involved in building machine learning pipelines perform cross-validation. And cross-validation is defined typically as a resampling procedure used to evaluate machine learning models on a limited data sample. And this kind of procedure has a parameter called K that refers to the number of split or groups that you obtain from your original dataset. And just to give you an idea, you can combine the two things, namely cross-validation and hyperparameter tuning, using this class in scikit-learn called grid search cross-validation. And the grid search cross-validation works as follows. Here, I'm taking this image from the scikit-learn documentation. So you have all the data, you split the data into training and test set, using the train test split method that we saw before. But then you split the training data into k folds, namely here is 5 folds. And the interesting fact is that first, at each single split, you train a model using different data, because in the first split you have fold 2, 3, 4, and 5 used to fit the model, whereas in split 2 you use 1, 3, 4, and 5, therefore 2 different sets. And then you use the blue folds to validate that model. At the end of the day, you have 5 split. For each split, you get a score. And then you take the average of that score to evaluate the model performance. And the beauty of using such method is that you first avoid possible bias from the splitting procedure, because each single data point is used at least one to perform a prediction. And therefore you evaluate the model at the end of the day using every time each single data point using the training. So this is a very consistent procedure and is typically done in practice. So my suggestion is try to master this concept by yourself. Today we are gonna basically use it as a simple example to see how to implement a grid search cross-validation inside a machine learning pipeline. So for completeness, I'm just gonna pick this machine learning pipeline that we defined before, and then I'm gonna import from the model selection, I import the grid search cross-validation class, and I define inside the variable CV nothing more than the grid search cross-validation object. And in particular, I pass four arguments, sorry. I pass the machine learning pipe that we define here. And then I need to specify the parent grid. And therefore, a natural question is, what is a parent grid? Parent grid is nothing more than the set of values that I want to specify for my parameters. Remember, I said I want to check different values of alpha in order to understand whether the model that I get is good, is the best one, namely the one with alpha equal to 1, or if there is another model with a different alpha for which I obtain a better model. And so to do that, what I can do is I'm going to specify inside a Python dictionary a grid for my alpha. And in particular, I'm going to use the log space from the NumPy library. And I say, well, I'm going to take 10 possible values, defining the log space between -3 and 3. And be sure that if you're using the pipeline object, you want to say, well, I want to check, I want to perform a grid search for the ridge model, and therefore I have to say that that alpha must be looped inside the step called model. And then you separate the model step name and the hyperparameter name with a double underscore. Then you basically can specify other arguments. The most important one is the CV that controls actually the number of splits. And in our case, we want to have, for instance, 10 cross-validation faults. In the example that I showed before, was CV was equal to 5, and that is the default of this function. And once you define that, you just need to fit a model using the xtrain, and the ytrain. Right? So let's try to run this. Typically, when you run a grid search cross-validation, it is lower than a normal fit because it has to learn different models. In our case, it has to fit the data on 10 different models. And at the end, you can pick the best model by accessing to the best estimator attribute. And therefore, you get a pipeline object with a standard scaler and a ridge model with alpha equal to 10. Remember, before was alpha equal to 1. Here you get an alpha equal to 10. So it's different. And that was thanks to the fact that we applied a grid search cross-validation. And therefore, you can see how was the performance on the best model by passing to the CV score method, the X test and the Y basically test. and you get a 0.665, which is slightly different from this one that was 668. It looks strange to me because actually this R square is lower, but possibly if you check instead the mean square error, that was 4.93, and now you get, let's see what we get. We can do this cv.best estimator.predict, and we predict with the X-test 4.943, which is a little bit higher, which is expected because we have a ridge model. But still, this score is pretty similar, but the third decimal is not exactly what I expected. In case you want to basically apply as last step to validate the model, you can actually apply the predicted directly to the best estimator, and you pass the X-test in this way, or actually you compute the score X-test and Y-test directly on that particular best estimator, and you get exactly the same score, namely by default, when you apply the score on the grid search cross-validation object, you get exactly the score from the best estimator. So I hope I gave you an idea of what we are going to cover during the webinar series. We're going to cover much more compared to this webinar. And in particular, I hope I give you an idea on how scikit-learn works. So if you enjoyed it, I strongly recommend you to watch our courses on scikit-learn in our content library, and obviously to attend the webinar series that is going to start in September 2021. So thank you for joining this webinar, and Francesca, it's up to you now.
Yes, thank you, Andrea, and thanks everybody. So we didn't receive any questions this time around, but we did receive several comments. People are really looking forward to joining this new series starting in September. So we're very excited to have you join us during this machine learning journey. Again, thank you to our audience, and thank you to Andrea. As usual, you know, we end the session with a couple of reminders, so you will receive the recording as soon as it is available. There is an end of webinar survey that we would appreciate if you could fill out. We deeply value your feedback, so any suggestions, any comments as to how we can improve, what kind of topics you want to see in future webinars, that would be much appreciated. Again, if you missed the initial announcement, we upload all of our webinars on cloudacademy.com/webinars. You can find all the previous sessions that Andrea led, so you will find everything there. And again, we'll start this new machine learning series starting in September. They're already on our website, so feel free to check them out and sign up for them. You will receive, of course, an email to promote them, and that's about it. Thank you for joining us, and until next time, goodbye, everybody.